Of all the talks I attended, the most interesting to me was the talk entitled Soft Matter, Food and Cooking. I found the information presented in this lecture extremely relevant, since one of my favorite hobbies is cooking. In fact, one of my favorite chefs of the Food Network, Alton Brown, says, "The kitchen's a laboratory, and everything that happens there has to do with science. It's biology, it's chemistry, it's physics. What actually happens to the food is all science." The speaker, Dr. Fernandez Nieves, did a great job of explaining aspects of cooking that I haven't really thought about much before in terms of physics and even chemistry. For example, usually when heating solid matter, the state is changed into liquid, or when heating a liquid, the state is transformed to a gas. Why then, when cooking an egg, a liquid, does it transform into a solid? He opened the talk with a discussion of soft matter. Examples of soft matter include liquid crystals, polymers, gels, foams, emulsions, and colloids. The speaker discussed mayonnaise in great detail as an example of soft matter falling into the specific category of emulsions. Before this talk, I had never really thought about how mayonnaise was made or why it had certain properties. Mayonnaise is an emulsion because it contains immiscible liquids, egg yolks, oil, and vinegar. Mayonnaise is made by slowly adding oil to a mixture of vinegar and egg yolk and stirring rapidly. If the egg did not contain a natural emulsifier, however, the two liquids would separate into distinct layers. The result is a soft matter. The mayonnaise appears to be a solid, but when spreading it onto a sandwich, it seems to have characteristics of a liquid. Next, Dr. Fernandez Nieves explained what elastic modulus was and how it determines certain properties of matter. The elastic modulus determines how stiff a material will be. The speaker makes a point about the importance of the units in elastic modulus. It is determined by dividing the force applied divided by the area of the material that the force is applied to. Some food happens to make up a diverse group of soft materials because food incorporates a variety of length scales. Upon doing further research, I learned that for smaller length scale molecules, shorter times are needed to reach equilibrium, but for longer length molecules, longer times are needed to reach equilibrium, therefore the kinetic equilibrium is reached. For example, representing a small molecular length, water is the most commonly used solvent in foods. The presence of hydrogen bonds in water lead to the clustering of molecules that is usually lost in larger molecules. Water molecules also have the ability to hydrate molecules that can participate in hydrogen bonding as well. Proteins are an example of a large-scale macromolecule made up of repeating chains of amino acids. The speaker discussed the science of cooking proteins such as meat and eggs. The reason that the egg becomes solid after being cooked is because the proteins are denaturing or unwinding from their quaternary and tertiary structures. He talked about how chefs understand that the secret to cooking delicious meat is by denaturing the correct set of proteins, so the meat is cooked thoroughly yet still very flavorful. The talk really inspired me to think more about the physics of cooking while I am in the kitchen. It opened my eyes to the diversity of food and how food is combined and transformed during cooking. In addition, I was educated about what soft matter was and how many types of food are examples of this unique subset of matter. Thank you for listening.